Alright, so last time we talked about semidirect products involving an automorphism alpha, and I guess at that point I shouldn't have yet called it a semidirect product, but the reason why you would call it that is because of this proposition that we are going to prove in this video, and hopefully we have time to finish it in this video. Typically when I say that, that means that there's not going to be enough time, but we'll see what happens. So let's see here. Let H and G be groups. We're going to let alpha be a homomorphism from H to the automorphism group the automorphisms of the group N. And we're going to let G be H alpha semidirect product with N as we defined last time. Then it turns out that G is the semidirect product of H and N in the normal sense. Well, I shouldn't say normal because this is group theory, and so normality is it has its own special meaning. So this is in the sense of how we define semidirect products beforehand. I.e., when we say this, we mean that H is a subgroup of G, N is a normal subgroup of G, H intersect N is trivial, and H times N equals G. And another thing in this video, I'm going to be really fuzzy about equals versus isomorphic. I think even here is an example of a time where I'm saying equals, but I really mean isomorphic. But whatever. This is group theory, and it seems like in group theory you don't really care about the difference between the two, unless it's not obvious that two things are isomorphic. Anyways, so conversely, if G is the semidirect product of H and N, then there exists an alpha in homomorphisms from H to automorphism group of N, such that G is H alpha N. And so one thing that we're going to want to keep in mind when we're doing this is that when we're talking about H semidirect product with N and H semidirect product with alpha of N, these sets, they look the same set-wise. They're both, well, actually, no, they don't, because when we have the semidirect product with an alpha, the underlying set looks like H cross N, the set direct product, where you just take things like you've got like ordered pairs with one element in H, one element in N, and then the product, the composition law, is that thing that we talked about last video. Whereas here, the elements look like H times N, so it's just a product of two things, and then the product in the set is just you take H1x1 times H2x2 is just H1x1 H2x2, and of course the fact that Hn is one of the things about this is that Hn is a group. We know that there is a way to write that H1x1 H2x2. There's a way to write that as an element of Hn. And that actually in and of itself is very interesting and kind of shows the relation between these. Anyways, or kind of shows the relation between semidirect products and just normal, regular. Is regular something group theory? I don't think so. Just regular direct products. Regular direct products. For this, to prove, so we have to prove that H is a subgroup of G here, in this sense. So, yeah. So H comma En the collection of all things like this. Is this right? Let's see here. So H and G are two. Oh, this should be N here. So I think what I want here is H times En, such that H is an H. Let's see here, this. Hold on, give me a second here. Did I mess this up already? No, I was right before. Let's see here. If we look at HEN, H and H, right, okay, so G is, okay, yeah, of course. So G here, G is H semidirect with N, so G, elements of G look like H comma N. So the underlying set for G is the ordered pairs like this. So this is good. Okay, cool. So we're good. We're on the right track. And we're running out of time. So this, certainly it contains EHEN, which is the identity, is closed under inverses, because if we take HEN inverse, we know from last time that the formula for this is H inverse alpha HEN inverse. Yeah, I guess. So this is that right? Right, so the inverse turns out to be, yeah, alpha H En inverse, right. And so now this is, but alpha H of En inverse alpha H is an automorphism, En inverse is just En, and so this is going to be just H inverse En. And this is this is going to be in there. And it's closed under, what's the other thing that's not inverses? Multiplication in the group, because H1En times H2En is going to equal H1, H2. Then we have this alpha H2 inverse En. Which of course again is going to be H1, H2, comma En, for the same reason as before. So G contains as a subgroup H comma En, H and H, but then this we can see is isomorphic to H cross En. So here I decided to be careful with my isomorphisms. But yeah, this, if you look at the composition law, you see that this is literally just, that even though we have this really weird composition law coming from this alpha semidirect product, it turns out that when we're using that product on this set, it works nicely, and it's just multiplication in H. So this is isomorphic to H cross En, and that's just H. So H is a subgroup of G. Likewise, by the same argument, but I'm not going to do it because it'd be literally the same thing. N is a subgroup of G. For normality, if we take some h1x1, multiply it by some element of n, where here, this is how we write elements of n as a subgroup of G, and then we conjugate by this and this, then this is going to be, this times this together, it's going to be h1 times E of h, which is just h1, and then just some other thing is going to go in the other thing, in the other place, and then times, what do these inverses look like? We're going to have h1 inverse here, we're going to have h1 inverse here, and then we're going to have just some other stuff in this other thing. The dot means it's just something, and it turns out we're not going to care what that is, because this is h times h inverse, this is e h, and then something. But since this is of the form eh and then something, this is obviously going to be something in n. And so then this is going to be in n. Where here, because this is what the elements of n look like. Okay, so next, if we take any h and x and g, h comma x and g, we can write hx as h-e-h, alpha e-h, e-n, x, and of course this is just a fancy way of writing h-e-n times e-h-x, which is an hn, and so g is equal to hn, because this proves that g is contained in hn and hn is contained in g, obviously. Okay, clearly, h intersect n is going to be just the element en, because when we look at these as subgroups of G, h is just things where like you have h here and then you fix en, and then n is you have eh here and then you can have this be anything in n. And when you intersect those two, you're just left with the identity here and the identity here. So they're intersection trivial. So thus, G is the direct product of h and n in the sense that we talked about before. So conversely, suppose G is the semidirect product of h and n. Define alpha from h to aught n, and this is actually kind of interesting because we're gonna show an actual homomorphism that works, and it turns out to be conjugation. Alpha h of x is hx h inverse, and this is sort of underlying the idea of semidirect products. But anyways, let's check that alpha is in hom h aught n. Okay. So alpha h for any h, alpha h of x1, x2 is, this is hx1, x2, h inverse. But then here, of course, we can throw h inverse h in the middle, as we like to do, and this is just alpha h x1 times alpha h x2. So alpha h is going to be in aught n as desired. And clearly this is going to be a map from n to n, because alpha h is, you plug in an element of n and then you get conjugation by n, but n is normal, and so there you go. Okay. So then alpha H1 H2x is, this is H1 H2x H1 H2 inverse. And this is H1 H2x H2 inverse H1 and inverse. And then from here you should be able to see we have H1, and then on the inside we've got alpha H2 of x, and this times H1 inverse. And then here we're going to get alpha H1 composed with alpha H2 of x. And so, indeed, alpha is a homomorphism from H2 aught n. Okay? Next, we're going to define a map eta from H semidirect with alpha n to G equals Hn. Of course, we can define this now because this is alpha is in the desired place and H and N are groups in and of themselves. And we know G is equal to Hn because we're assuming that G is a semidirect product of H and N. And we're going to do this by eta of H of x equals Hx. I claim eta is an isomorphism. I don't think I'm going to be able to fit this all on this board, but anyways. Yeah, let's actually go ahead and erase some of this real quick. Okay, so eta of H1 x1 times H2 x2. Well, this is going to be just eta of, we do that horrific composition law here. And so then this is going to be H1 H2 times alpha H2 inverse x1 x2. But now this is going to be, because we know what alpha is, its conjugation. So alpha in H inverse x1, H2, x2, and then the H2's cancel. So this is H1 x1, H2 x2, which is just eta of H1 x1 times eta of H2 x2. So eta is a homomorphism. Surjectivity is clear because G is equal to Hn, which if you take any element Hx in there, this is going to be eta of Hx. For injectivity, let's see here. If eta of Hx equals Eg, this is going to imply H of x equals Eg. So that's going to imply that x is equal to H inverse. But this is an H, and so if x, so then x is in H intersect n, which we know is just the identity element, and so then, and of course this is the identity in E, but anyways, so E is equal to x, which is equal to H inverse. But if H inverse is the identity, then H inverse is equal to H, and so Hx equals EH En, because they're both just the identity element. Hence eta is an isomorphism. And so that means, because this is an isomorphism, that it means precisely that we actually have what we wanted. We have that this is a G is isomorphic to H semidirect product with N. So I guess that's really what we wanted, that G was isomorphic to H semidirect product alpha with N. And let's see here. Now that I have like an extra minute or so, I think somehow I managed to speed through this really quickly. I think the really interesting thing about this proof is in this calculation, because this shows you the relation, the group action relation between the two groups here. And so, like, what's happening is where this product comes from is if you multiply it together, and if this happens to be conjugation, then that allows you to get rid of this H2, and you get to take this X1 and bring it over by the H1. And so that's the real issue with semi-direct products. Now, if this is a direct product, then everything commutes. And so instead of having to, like, if you wanted to do like if you had like H1, H2, X1, X2, then right, if you had like H1, H2, X1, X2, then you could just move them around. I don't know. I don't know if I'm quite explaining myself well, but there's something really important going on here. In some sense, this alpha allows you to like go from having all of your H's together and all of your X's together. This alpha allows you to put these ones together and put these ones together. So I'm sure there's a much more precise way of saying that, but in some sense this tells you how that works. But anyways, we're done with this, and there we go.